All right, now we're in section 5.7. We're going to talk about, so you've learned about the substitution approach to help find antiderivatives, for integration. And then you learned about, in section 5.6, the integration by parts approach. And there are other ways, other approaches that can be used to help you find antiderivatives. And in this first example, we have what's called a trigonometric integral. Okay, so let's see here. So we have the integral from 0 to pi over 2 of the cosine of x to the 5th power dx. So remember when we write it this way, this is just its notation. This here, this notation means the cosine of x raised to the 5th power. Cosine of x raised to the 5th power. Okay, so let's see. We got to do something here. We have to do something to help us. And we do know, for instance, that what's the sine squared of x plus the cosine squared of x equal to?
1.
That equals 1. Good. Good. D'Angelo, good. Sandia, good. Javier. That's right. And of course, we recognize that on the left here, this is the same as, it's notation for the sine of x quantity squared plus the cosine of x quantity squared equals 1. That's a trig identity. Appendix C in your textbook at the end has it's a review of trigonometry. This is that famous Pythagorean identity. Now, the reason I talk about that is I've never seen the cosine of x to the 5th power in my trig identity. So I wonder if I can break that down so that I could use maybe one of the identities above to help me. And that's what we're going to do. So look at what we do here. All right, here we have the cosine of x to the 5th power, and I'm going to write that as the cosine of x squared times the cosine of x squared times the cosine of x. I can write this trigonometric integral this way. Now, why would I want to do that? Why would I want to do that? Well, I want to try to make a substitution. I want to see if I can make a helpful substitution so that I can find the antiderivative. Well, we recognize that when we have the cosine squared of x, okay, since sine squared of x plus cosine of squared of x equals 1, okay, that means that the cosine squared of x would equal 1 minus sine squared of x. And so these two cosine squared of x terms can be replaced by 1 minus sine squared of x. Okay, and that's very helpful because now we can make a substitution. We can make a substitution that's going to work. We're going to let u equal the sine of x. If we do that, Well, then in this integral above, we're going to have 1 minus u squared times 1 minus u squared. And the cosine of x dx will turn out to be du. Because if u equals the sine of x, du will be cosine of x dx. The limits also have to get changed. Okay, and this whole integral with respect to x is going to become this integral with respect to u. The 1 is the cosine of pi over 2. And the 0, that comes from taking the cosine of, sorry, hold on now, I got to be careful here. No, I have that wrong. The 1 is because the substitution is u equals the sine of x. So 1 is the sine of pi over 2, and 0 is the sine of 0. That's how I get those limits. Okay, and so here we are. Are there any questions on what we did here? Okay. Well, so we have 1 minus u squared times 1 minus u squared. And if we FOIL that out, we're going to get 1 minus u squared plus u to the 4th. And so now this trigonometric integral just becomes this integral. The integral from 0 to 1 of 1 minus 2u squared plus u to the 4th du. And now that's a calculus 1 problem to get that antiderivative. Please let me know if you have any questions. Okay. Please let me know if you have any questions. Justin, how are you feeling about that? So I'm just going to kind of call out a few names while people are. Justin, are you feeling good with that?
Yeah, I guess that the more times I practice this, the more it'll be more clear to me.
Sure, I understand. Okay, very good, very good. Jan, how about you? How do you feel about that? Are you
Yeah,
comfortable?
yeah, I think I'm
Okay,
good with it for now, yeah.
okay, good, good, good. All right. All right, well then let's go to the next page. If there are no, want to make sure I'm pacing myself well, or we're ready to go to the next page and finish the problem off. Okay, David's ready. Okay, so here we are. we'll get the antiderivative of, 1 minus 2u squared plus u to the fourth. The antiderivative is u minus 2u, the antiderivative is u minus 2/3 u cubed plus u to the fifth over 5. And now we put our limits of 1 and 5 and 1 and 0 in there. And we work it out and we'll get 8/15. Absolutely amazing. Okay, let me know if you have any questions.
Professor? Professor?
Yes, Ange.
How can we recognize what we can use? Because this is substitution, but is a whole lot of new technique that is it specific to that particular integral, or
Well, it does work. It does work for that particular integral. And in your homework, you're going to have a variety of these kind of problems where there's going to be help aids available. Let me just hold on. It's a good question. Let me just look at one thing here. One moment. Right. So yeah, I'll show you something in the whiteboard here. I'll show you something in the whiteboard. So let's say you had something like this. Let's say you, whoops, hold on, I don't know what that is. Hold on. Oh, I don't want to do that. Okay. Let's say you had the integral of cosine squared of 6 theta d theta. Let's say you had something like that. And you want to get the antiderivative for that. Well, this one here, see, cosine squared is like as basic as you get. It's not like we're taking cosine to the fifth and we're breaking it down into cosine squared, and cosine. Where cosine squared is like, a basic, so to speak. So how are we going to handle that? Well, there is a trig identity that says the cosine squared of 2x. Okay, hold on. No, that's not what I want. Cosine squared of x. Does anybody remember what that equals? If you think about your trig identities, cosine squared of x is, what would that be?
One plus sine squared x.
Okay, 1 plus, hold on here, one moment. I was hoping, let me just see here, one moment. I was hoping you would say this. Let me check the back of the textbook. Yeah, Xavier, that's what, so Xavier's getting that. Now, I'm not saying there aren't other equivalent trig identities, but certainly this is one of them. Certainly this is one of them. And if we, let me just see here, hold on. Let me come back to this. Let me go to the textbook. Hold on. Go to the ebook here. Hold on, I want to make sure I'm all right. Let's go to the hold on. Yeah, here we are. So if you go to the appendix here and find Appendix C, is it? I can't tell if it's showing up for you or not. It's not showing. All right, hang on. Let me just find it here separate. Gosh darn it. Hold on. Give me one moment here. Got too many windows open. Too much stuff open here. Hold on. Okay, let me bring up that ebook. Share application. Okay, so the ebook is showing, right? Good. Okay, ebook showing. So if you go down to appendices, click on that. Okay, and you have a lot of appendices. You have a lot of appendices, and you want trigonometry. Appendix C. So a good review of trigonometry here in Appendix C. And I'm just going to find here the identity. Again, really a very nice review of trigonometry. And there's some identities. Let's see here. Here we go. And there's an identity for cosine squared of x equals 1 plus cosine of 2x over 2. Okay, so on the exam next Thursday, I would give you that identity. Okay, you wouldn't have to memorize that identity. Any engineer could look up an identity, and I want you to have access to that. I don't want you to get a problem wrong because you don't remember an identity. Okay, like that. Are there any? How many might use this Appendix C to review? To review their trig a little bit. Okay, good. We're getting a number of folks. Wonderful. So it's in your ebook, and the physical textbook would have it in the back as well. So Appendix C, trigonometry. I didn't have a chance to see all the chats, but excellent, wonderful. All right, so let me go back to that whiteboard. And I wish they'd have they always seem to remove the problem. But the problem was the integral of cosine squared of 6 theta. Okay, it's optional to put that in the parentheses, but I will. And again, here, to do this problem, you'd want to make use of the fact that the cosine squared of x is 1 plus the cosine of 2x over 2. Well, so 6 theta is the same as, hold on here. Well, that's your x, right? So then you could write this as 1 plus the cosine of 2 times 6 theta all over 2 d theta. And so this would be then the integral of a half plus cosine of 12 theta over 2 d theta. And the half, actually, I can bring that out front. And so then I'd have the integral of 1 plus cosine of, one moment. Yeah, 1 plus the cosine of 12 theta d theta. And then you would break this up. Hold on, I'll get to that question. I won't show you the whole problem, but I'll show you, you know, I mean, well, I guess I can. You would break this up into 1/2 times the integral of 1 d theta plus the cosine of 12 theta d theta. How did I get the, okay, Mario, you're good on that, on how I got the, so how did I get the 12 theta? Well, this is the standard formula here. This is the standard trig identity, cosine squared of x equals 1 plus cosine of 2x over 2. So I'm going to let 6 theta be my x. And so I get 1 plus cosine squared of 2x over 2. Well, 2 times 6 theta is 12 theta. Okay, good, good, good. And then, you know, you just integrate this. You just integrate this. And if you did that, you get 1/2 times theta plus the sine of 12 theta over 12 plus a constant. Okay, that would be your answer. And then you can distribute the 1/2 through. So you see, that's how you'd have to handle that kind of problem. So it really depends on the problem. It really depends on the problem, what you have to do. Are there any questions on that? Okay, okay. Okay, Sandia is good. All right, thank you. Thank you, Mario. Okay, Sandia is comfortable. Okay, well then let's go back. So there are other types of integrals too that are important. And if I look here at this section 5.7, if I look at it, okay, here's another integral that's very important. This kind of integral is going to come up in differential equations. How many have to take Math 282 here? Differential equations. Okay, Ange has to, and okay, Mario, all right. Well, and I'm sure a number of you will. Kiddis, okay, very good. And Elmer, and so this kind of problem will come up when, for instance, you're working with what are called Laplace transforms. Okay, and so let me give you a moment to copy the example down. Okay, so what we have here is we have a rational function. A rational function. And we want its antiderivative. And incidentally, so initially you might say, okay, if I were to try to substitution, what would you try letting u equal if you were to try a substitution?
2x squared plus x minus 1.
That's right. But if you let that, if that's right, Ange, if you let u equal 2x squared plus x minus 1, then du dx would equal 2 times 2x plus 1, which is 4x plus 1. So du would equal 4x plus 1 dx. But the problem is we don't have 4x plus 1 dx here. We have 5x minus 4. Okay, and so that means substitution won't work. Okay, and yet this kind of integral is very, very important for us to be able to solve. So what we really need to do is we need to rewrite this integrand here, the 5x minus 4 over 2 squared plus x minus 1. We need to rewrite it in a nicer way. And what do you notice, interestingly, about this denominator? 2x squared plus x minus 1. Is there anything that's interesting about that denominator?
It's factorable.
That's right, Koch. It's factorable. And you've been kind of trained in math. If something can be factored, you factor it. And that's going to be helpful here. So let's go to the solution. Well, incidentally, what are the factors? I mean, before we get there, what are the factors? So 2x squared, the only way you can get that is a 2x and an x. So what's going to go? What's
2x
left?
minus 1. And
2x minus 1 and x plus 1. I agree. I agree. So if you FOIL that, you will get 2x squared plus x minus 1. Good, Taj. And so let's go ahead here then and pursue on. That's right, Sandhya. Whoops, hold on. So certainly I can rewrite my integral I as the integral of 5x minus 4 over 2x minus 1 times x plus 1. Certainly we can do that. And what we have here in the denominator, the 2x minus 1 and the x plus 1 are what are called linear factors. Because if they're of degree 1, quadratic factors would be of second degree. You'd have to have an x squared power for a quadratic factor. But a linear factor, the x is a factor where the highest power is x to the first power. And it turns out, interestingly enough, we can write this this rational function as the sum of some constant a over the one linear factor, 2x minus 1, plus another constant b over the other linear factor, x plus 1. We can actually re-express that rational function as the sum of these two little other rational functions. Now, in order for us to say that, to be able to do that, well, we would need to show that there exists a constant a and a constant b such that this would work. So I'm going to show you how we can get that. let's first of all, let's say, okay, I'm gonna rewrite the rational function 5x minus 4 over 2x minus 1 times x plus 1 as a over 2x minus 1 plus b over x plus 1. Let's just say we can do that. Well, if we can do that, I ought to be able to solve for a and b. So how am I going to solve for those constants a and b? Well, I'm going to multiply through the equation by 2x minus 1 times x plus 1. That's my least common denominator. How many remember that from their pre-calculus days? Working with rational equations and multiplying through by the least common denominator. Sure, Ange remembers that. Yeah, you know, and that's going to break this rational equation down to an equation that, and Sandia remembers algebra too. Absolutely. Absolutely. So, okay. Well, all right, I'll multiply through by my least common denominator. I'll multiply through the rational equation by my least common denominator, which is 2x minus 1 times x plus 1. And then some nice things are going to happen here. That's right, Sandia. Well, okay, so we're going to get some simplification here on the left. And that's going to leave me with 5x minus 4 on the left. And then on the right-hand side, well, now let me just see here. I want to be careful here. I should have a, I don't really need this parenthesis here, right? I don't really need that there. That should be like a small parenthesis, right? So one moment, let me just fix that in my notes too. Okay, and so more nice things happen, more simplification happens. Okay, and then more simplification here. And so that's going to give us then this equation here at the bottom. Are there any questions on that? All right. Well, now what we're going to do is we want to solve for A and B. We want to figure out what those constant values are. So I'm going to distribute the A through the x plus 1, and I'm going to distribute the B through the 2x minus 1. And when I do that, okay, when I do that distribution, that's going to get me 5x minus 4 equals a times x plus a plus 2bx minus b. And what I'm going to do is I'm going to group together like terms. So what I have here, right, is ax, a times x, plus 2 times b times x, plus a minus b. But the a times x plus 2 times bx can be written as a plus 2b times x. And so now I have an equation. Where the left side, you know, in order, I mean, the 5x minus 4 on the left must equal what we have on the right. So that means, for instance, that this 5x here, this 5x would have to equal the quantity A plus 2B times X, right? In order for the left side to equal the right side of this equation, the X terms have to be equal. Okay, it's like an analogy, quick analogy. If you had like 2 plus, no, if you had 2, let me see here, hold on. If you had A plus B times X equals 3 plus 5X. Okay, this is just a separate thing now. Then what's A going to equal? If A plus B X equals 3 plus 5X, what would A equal?
3.
A would have to equal 3, and good. That's right, Ange, and B would have to equal
5x.
5, right? So very simple example, but it's the same kind of principle. A plus 2B would have to equal 5, and then the -4, that constant term would have to equal the constant term on the right. And so A minus B would equal -4. And so you end up with, okay, so you end up with here, let me just see here. Let me just kind of, I want to circle. This here means implies that double looks like a line, looks like an equal sign with an arrow. That means implies. So A plus 2B must equal 5, and A minus B must equal -4. Okay, and so I have 2 equations and 2 unknowns, right? That's algebra 2, right? So what I'm going to do is, if I want to cancel the B terms out, I'm going to multiply through this second equation by 2. And so I'll get this result here. A plus 2 times B equals 5, and then 2A minus 2B equals -8. I'll add both of the equations. And so that then will, the B terms cancel out. 3A equals -3, A equals -1. If A equals -1, then, all right, then algebra 1 and 2, right, Cynthia, right? And now it's coming back. So you learned that a long time ago. Maybe you haven't seen that in a while, but now it's coming back. A equals -1, and systems of equations, exactly right. That's right, Cynthia. So the second equation was, right, is A minus B equals -4. So when A equals -1, I'm going to substitute that back in the second equation. I could have substituted in the first equation also. I just chose the second equation. So -1 minus B equals -4. That means B will equal 3. And now I'm able to write my integral as this integral here. Okay. We're not done yet, but are there any questions? Okay, well, so we have, so of course, the -1 is the A, and the +3 is the B. And now we're ready to proceed on. So we have the integral of a sum here, right? Well, that's the sum of the integrals. So let's proceed on. Step by step, step by step. Okay, and so I have two integrals. I factor the 3 out of the second integral. And look here, I got two little substitution problems. Two little substitution problems. And I factored a -1 on the first integral. The first integral, I'll let u equals 2x minus 1. The second integral, I'll let w equals x plus 1. Okay, and so with those substitutions, now the 2x minus 1 is w. The 1 dx here is a half. No, it should be u, right? 2x minus 1 is u. And the 1 dx is a half du. And then the second integral, the x plus 1 is w. And the 1 dx is dw. And so that gets us down here. I mean, this is pretty cool, huh? We're not done yet, but are there any questions? Okay. Well, then let's go ahead and finish this problem up. What's the antiderivative? What's the antiderivative of 1 over u? I'm sorry?
Alan, the absolute u.
That's right. That's good. Good, Ange. The log of the absolute value of u. Okay. And so here we go. And remember, this integral was our original integral was this. The original integral I was equal to the integral of 5x minus 4 over 2x squared plus x minus 1 dx. So for our final answer, we have to put well, u was equal to 2x minus 1, and w was equal to x plus 1. So we got to put those back in. Now, if it were a definite integral, we would just put in the u and w limits and compute it. I still see some times, maybe videos or even other professors going back to put in their original limits. And I always kind of ask why you want to do that. I mean, when you're doing the definite integral, why not just, work with your new limits, but, here we go. So there's the answer. Absolutely amazing. Absolutely amazing. How many find this really amazing? Yeah, Jing Sung likes it. Sandia likes it.
It's pretty tricky. It's all the quadratic integral will be solved the same way, or
Well, right. So your instincts are good, Ange, and I'll maybe show you this on the whiteboard. It's a bit challenging. Yes, Xavier says it's amazing if you get the right answer after you're done. Then I hear you. I hear you. Let's say, let me just, I'm going to go to the whiteboard for a moment here. Let's say you had this. Are there any questions on this one? On the answer? Okay, let's go to the whiteboard for a minute. So the trick with, and by the way, actually, hold up. What we did here, hold up here, one moment. Yeah, so this by the way, you want to have for your note. When I said in the notes that for this example, the expansion, I can add the words partial fraction expansion. Okay, expansion. What we're doing, you're solving integrals by the method of partial fractions. Partial fractions. Okay, so let's say you had something like this. Let's say you had the integral of 3x minus 1 over x squared plus 2 times x minus 1 dx. Okay, so what you're going to have to do is, and remember, in these problems, you always have to factor the denominator. So sometimes in WebAssign, the problem will be factored. Sometimes it won't. You have to make sure it's completely factored. So here, okay, you have partial fraction expansion where you have two fractions. What's going to go over the second fraction, the x minus 1? What would we put there? Well, this factor here, x minus 1, is it a linear factor or a quadratic factor?
linear.
It's linear.
It's a linear factor. Okay. The x squared plus 1 on the first fraction, what kind of factor is it? Is it a linear factor?
quadratic.
No, it's a quadratic factor. Thank you. It should be x squared plus 2. Thank you. Thank you. Thank you, Sandhya. That's right. Let me just, this should be x squared plus 2. Okay, good. This here is a quadratic factor. Now, quadratic factors, we're not going to put constants above a quadratic factor. What we are going to put is a linear factor above. A times x plus b. That's a linear factor. So whenever you have a in the partial fraction expansion for this particular rational expression, because there's a quadratic factor, above the quadratic factor, we put a linear factor, a times x plus b, which is 1 degree less than the quadratic factor. Above the linear factor, we're going to put a constant, c. A constant c is 1 degree less than a linear factor. The linear factor has degree 1, right? Well, a constant has degree 0. So that's how, that's kind of a good rule to remember when you do your partial fraction expansion. And of course, on Thursday's class, we're going to do some more examples for this partial fraction expansion. We're going to do some more examples, but you've seen here just sort of like, you know, we went through a basic one. Okay, give me one moment here. One moment, class. Are there any questions? Any questions on that? Okay, one moment, one moment. Just give me a moment here, class. If there are no questions, I'll stop the recording. Okay.